Okay. What is the equation 1 over g of x if g of x equals x squared minus 4? 1 over x squared minus 4. So the reason why the x-intercepts of the original equation turn into asymptotes, we can relate it back to rational expressions, right? When you have a rational expression here, how do I get the non-permissible values? We factor. And what does that factor to? And so x can't be equal to plus or minus 2. And that because you cannot divide by 0. So those NPVs are asymptotes. Boom. They're related. Okay? It essentially is an NPV. That's what your asymptotes is. So we're going to draw a vertical line at -2 and +2. Uh-oh. Uh-oh. 1 second. Seriously? Why? Okay. 1 second, guys. Oh, knocking my wires off. Is it in? Right. Okay. Again. If you need to do little squiggly lines, that's fine. I don't understand it because I've never seen that before. I've only ever seen them in all my math career as dotted lines. They're not that hard to draw. Winter, I tell you, hey? Okay. Now it's helpful when you to draw your original graph and then draw the reciprocal. So let's do that. It helps if you have different colored pens. I don't know if you've noticed that. Okay, the graph of x squared minus 4. So it had x-intercepts of plus and minus 2. We just factored that, right? When you y is 0, that was at plus or minus 2. So those are my x-intercepts. Okay, where's our vertex of this graph? 0 and -4. Our a value is 1. So our pattern would be 1 over from the vertex, and then how much up? 1 up. 1 over, 1 up. 2 over, 4 up. 3 over, 9 up. So that'd bring us to 5. Okay. So that's the original function. Ooh. Sorry, my drawings suck. Not easy to do a good job. Okay, so we want to draw the reciprocal of that. I can make it larger for you. Is that better? Much better?
What do you have on the right side? Is it equal 1 up 1 to the right?
This is equal.
No, on the right you have something red.
Oh, over here? I just have, sorry, the vertex. And the x-intercepts.
It's 1 up 1.
1 over 1 up? Or which?
It's really together.
Yeah, because a is 1. The a value is 1. So it's just the normal x squared, right?
Yeah.
So 1 squared is 1. So 1 over 1. 2 squared is 4. 3 squared is 9. Okay, from your vertex. Okay. So let's draw the reciprocal. Now, I want to draw the invariant points. Where are the invariant points? Oops. When y is negative and positive 1. So I'll take this away later, but we want when y is positive and negative 1, where the graph crosses that line, those points are going to stay the same, right? Get over here, maybe. Okay, so where y was 1 and -1, uh-oh. There we go. Okay, that's where our variant points are going to be. So we're going to have a point there, there, there. We're approximating, right? As close as we can on the line of 1 and negative 1. What was another important point on the original graph that we can try and do the reciprocal of? The vertex, sure, or the y-intercept. So the vertex was at negative 4. So what's the reciprocal of that going to be? Negative 1/4. Okay, I'm going to get rid of these lines now. Oops, undo. 0. Let's move that out of the way. Okay, so back to drawing. We can now do the point 0 and negative 1/4. About right there. That's your name. How do I get that again? Okay, the y value was negative 4, so we took the reciprocal of negative 4, which was negative 1/4. Okay? Okay, thank you. All right, are there any other points we could take the reciprocal of that we have? Yeah, sure, the points. So 3 and 5, what is 3 and 5 going to become? 3 and 1/5. We take the x stays the same, we just take the reciprocal of the y value. So that coordinate was y value of 5 turns into a y value of 1/5. X stays the same. Okay, same with on the other side, negative 3 and 5 becomes negative 3 and 1/5. Okay, how about negative 3? Or sorry, negative 1 and negative 3 becomes negative 1 and negative 1/3. And same with on this side. So we take the reciprocal of the y value. Whatever the y value is, take the reciprocal of it. Okay, does that give you an idea what this graph is going to look like? No? Okay. Well, let's think about what we know. Okay? I need oh, here's a magic pen. That's good. So as we approach this 0, as that point, that original graph approached 0, our graph is now going to approach infinity. We're going to approach our asymptote, right? It's going to get really large. And where the original function was getting larger, we're getting closer to 0. Oops. Not supposed to go up there. Closer and closer to 0. But not touching it. Sorry. Should almost make it bolder. And same, so here, like you're gonna notice how where your y values were above the x-axis, you're still above the x-axis, your reciprocal. So this portion between negative 2 and 2, notice the y values were below. Yeah, Avery?
Can you re-explain how you get those points?
Okay, re-explain how I got the points. Okay, so see how, like for example, this point right here, negative, that point right there, okay? That point was 0 and negative 4. Okay, so the reciprocal is going to turn into 0 and negative 1/4. This point here was originally 1 and negative 3. Will turn into 1 and negative 1/3. So we're just taking the reciprocal of the y coordinate. The x stays the same. Okay, good. That's good to hear. All right, so this part's going to go down and approach our asymptote. Why is it like that? We'll talk about that in a second. It's hard not to... You have to erase everything? Oh, that's not good. I'm just going to take this and make it gray. Instead of green. Okay. All right. and the other side. Okay, so let's talk about why does it do this. So notice where I was above the x-axis, I'm still going to stay above the x-axis. Okay, so here's the black line is the reciprocal. So where the graph was getting larger, the reciprocal is getting smaller. Where the graph, this is really close to 0, the reciprocal is close to infinity. Whereas our graph was close to 0, our graph reciprocal is close to, well, in this case, negative infinity. Okay, do you get the idea? Little bit? Little bit? Little bit. So, what are the equations of the asymptotes? X equals negative 2, x is equal to 2, and y is 0. Okay, we're going to cover very simple reciprocal functions where your horizontal asymptote is always y equals 0. Sure is. What is the domain? Can equal plus or minus 2, otherwise element of the reals. Range. Y can't equal 0, otherwise YER. Okay. Alright, let's put these lines back at 1 and negative 1. Yeah, I can. Tell me when. Okay. Okay. Before we start the next one, let's use our graphing calculator and see what it should look like, okay? Looks great? Okay. So, I should say, guys, that not all quadratics will have asymptotes. What? When you take the reciprocal. Why? Well, where are the asymptotes located? Where the original graph had x-intercepts. Is it possible for a quadratic to not have x-intercepts? Yes, of course it is, right? So for example, just really quickly, can you graph with me? Y equals, let's do x squared plus 9. Okay, because let's do x squared plus 1. Okay, x squared plus 1. Now, we have to do brackets, right? Okay, so x squared plus 1, it opens up y-intercept of 1. It won't have any x-intercepts. So when you take the reciprocal of that, it won't have any asymptotes, and it looks really cool. Graph it. Ooh, it's like a little hill. Just a little hill. Okay, so, right, let me graph the original graph. The original graph looks like this. Okay, x squared plus 1. Because it has no x-intercepts. With no x-intercepts, there's no asymptotes. Okay? Okay, guys, without x-intercepts, there's no asymptotes. Because the asymptotes are always located where your original graph had x-intercepts, because that's when y is 0 and the reciprocal of 0 is undefined. Okay? So for example, I'll do another one. How about we did x squared plus 4? Or let's do plus, I don't know. Yeah, plus 4. Okay, if you compare those two, let's graph them. The x squared plus 4 does not, see, it's even smaller. It's harder to see. That's why I did plus 1. But it's still a little hill. So where it's getting large, we're approaching 0 still. And then the reciprocal of our vertex, which is at 4, is 1/4. So you only get as high as 1/4. That's why it looks so tiny. What? What? Okay, where is the graph undefined? Plus and minus 3. It's your original x-intercepts, right? Which will now become asymptotes. I'm going to use, great. Or whatever squiggly line you choose to use. which is weird. Winter's weird. Tell him I said that. What? Okay, so there's the asymptote x equals 3 and negative 3. Let's graph the original function. So let's get some points on the original function. Tell me some of the points on the original function. Okay, so where's the vertex? Let's start there. Okay, it is in vertex form, 0 and negative 9. And negative 9 also happens to be your y-intercept. Gentlemen. Okay, what's the a value? 1. So we're going 1 over, 1 up, 2 over, 4 up, 3 over, 9. We've already done that one. 4 is 16. Negative 9 plus 16 is 7. Okay. So why do I draw the original function? What's one good reason? Okay, so you see you have the invariant points. You have points to actually take the reciprocal of. That's another reason. Oh, did we already say it? Did I say invariant?
Yeah.
Oh, yeah. Yeah, the invariant points. Yeah. The asymptotes. It also tells you the asymptotes. Where's my beautiful color? There it is. Oops. Bonus points for what? There's no such thing as bonus points in real life. No, in real life. Okay, so let's plot our invariant points. I'm going to use this ugly color. Okay, I'm plotting the invariant points. What are the invariant points when y is 1 and negative 1? So I highlighted where y was 1 and negative 1. And where the original graph crossed 1 and negative 1, I made those points. Oh, what happened here? I erased it. No. What happened? That's so weird. Okay, so I'll just do a different color. Lost it all. So here's purple. Okay, y equals 1 and negative 1. Let's take the reciprocal of some points. So negative 9 when y is negative 9, it turns into y as really close to 0. Negative 1 9. Yes, thank you. Negative 8 turns into negative 1 8 for both when x is 1 and when x is negative 1. You with me still? Yeah. Okay. Let's do the point of 2 and negative 5 turns into 2 and negative 1/5. Negative 2, negative 5 becomes negative 2 and negative 1/5. All right. So do we get the general shape of this bottom portion? Yeah. You can go ahead and connect. It looks almost like a straight line. And then what happens after that? Goes down towards the asymptote. Because our original graph was approaching 0 at that point. When it's approaching 0, the reciprocal of a really small number is really large. Okay? We have another point at 4 and 7. So that's going to become 4 and 7. 4 and 1 over 7. So really close to 0 there. And really close to 0 here. All right, do we have enough to draw it? Yeah. Because as x approaches negative infinity, y is going to approach 0. Get closer and closer to negative 3. Our y approaches, from the left side at least, positive infinity. beautiful? Isn't she beautiful? Okay, there you go. That's not so bad. Okay, what are the equations of the asymptotes? X equals plus or minus 3, y equals 0. Domain. Okay, nothing special. All right, let's turn the page. Get that down, turn the page. '20s. Invariant points are when y equals plus or minus 1. Because the reciprocal of 1 is 1. Reciprocal of negative 1, negative 1. Okay, so let's use our graphing calculators to find our invariant points. So you can use your graphing calculators to in fact find them. It's very simple. So we're going to type in this into y1, our function. Okay? 1 over, make sure you have brackets. Unless you have a fancy calculator that can do numerator over denominator. Or numerator over denominator. So if you have numerator over denominator, life is good. Okay? Yeah. Okay? So do you remember how to get numerator over denominator? Alpha y equals. Alpha, and then number 1. So go alpha y equals. Alpha y equals. Alpha y equals. Yeah. X squared minus 2x minus 3. Okay? Is yours does that? But you have a fancier, even fancier than everyone else's. Yes, yours does that. Yeah. Okay, graph your function. So we want to know when is y equal to 1 and when is y equal to negative 1. How do we do that on our graphing calculator? Okay, so let's set y2 equal to, we'll do one at a time. I find it a lot easier. One at a time. So set y2 equal to, let's start with 1. And find intersection. Yes. What calculator do you have? Then you're stuck with it. Sorry, Ellie. Yeah, if you zoom in, it gets a little better. Then it looks nicer. Because if we go second graph, we need when y is 1 or negative 1. Do you see it anywhere? No, right? So that's why. Okay? So that only works if it's a whole number. And usually it's not. Okay, so find the intersections. Second, trace 5. You have to make sure you get over there. So get near the intersection. Enter 3 times. Let's go to 3 decimal places. So what is that coordinate? Let's write it down. Negative 1.236, comma, 1. And trace 5. Scroll over to the other one. Won't let me hold it down. It's awful. There you go. Enter, enter, enter. We get 3.236, comma 1. Okay. But there's how many invariant points? 4. So now we have to set y2 to negative 1 and find those intersections. So it's less confusing for your calculator if you do one at a time. Instead of going y2 equals 1 and y3 equals, unless you turn off the equal signs. All right. second trace 5. Scroll over. Enter, enter, enter. Negative 0.732, comma, what? Negative 1 and is it 3 point something? No. 2 point something? 2.732? Okay, so there's your 4 answers. All 4 of these are our invariant points. Okay? Okay, so this first one, find the vertical asymptotes. How do I get the vertical asymptotes? When y is 0. So you can just take what were the original x-intercepts, right? When was y 0? How do we find that out? Someone said it, factor. 2 numbers that multiply to negative 6 but add to positive 1. That's 3 minus 2, so x equals negative 3 and 2. So those are our vertical asymptotes. Okay, invariant points. For invariant points, algebraically, without a graphing calculator, we're setting y2 equal to 1 and y equal to negative 1. So 1 is equal to x squared plus x minus 6. Let's start there. Uh-oh. This room is special. Okay, one side's a 0, so if I subtract 1, it becomes minus 7. Does that factor? Does not factor. Therefore, we use quadratic formula. Which does not simplify. We just get 29, root 29. Negative 1 plus or minus root 29 and 2. Okay? Well, it's 4 times 7 plus 1. Really wasn't giving you the answer, was I? Maybe. Okay, so those are 2 points. What are the 2 points from that we were given? So x was either negative 1 plus root 29 over 2 when y was what? Positive 1. We set y to 1. Okay, the other point was negative 1 minus root 29 over 2 at positive 1. Okay. All right, now let's do when y is negative 1. So if I add 1 to the other side, it becomes minus 5. Is it factorable? Nope. X equals negative b plus or minus the square root of b squared minus 4 times a times c. When a is 1, you don't really have to write that in, right? No? Okay, you can. No, just in the second part of a times 4ac. I don't know. Okay, so you get 20 what? 1 plus what? 4 times 5, guys. 20. 2 negatives and positive. So 1 plus 20 is 21. So that was when y was negative 1. There's our 2 points. Negative 1 plus root 21 over 2, comma negative 1. Negative 1 minus root 21 over 2. There's our 4 points. Okay, so yeah.
Do you ever have an example where one of the square roots will be negative, so you only have 2?
There is possible to only have 2 variant points, yeah. That example I gave you where there was no x-intercepts, right? A graph like that could have even only 1 invariant point. So that graph x squared plus 1 that we graphed, 1 over x squared plus 1, it had 1 invariant point because the vertex was actually at 1, and it went up. And so when you graph the reciprocal, it went like this, right? So it only had one. That's an example where it has one invariant point. X squared plus a half, the reciprocal of that would have 2 invariant points. So where it has no asymptotes, that type of example. Okay, other points. Let's just do the y-intercept. What was the y-intercept originally? 0, -6. So what will it become on the reciprocal? 0 and -1/6. X stays the same. We take the reciprocal of y. Good? Okay, last question. That wasn't so bad, was it? Tell me, was this originally a linear or a quadratic? Why is it linear? Okay, there's only 2 curved parts, sure. But there's only one what? Asymptote. And if there's only one asymptote, that means the original function had one x-intercept. Okay? And we also know it's linear because one portion is above the y-axis and one portion is below, just like a linear graph. On one side of the x-intercept, it's positive. On one side of the x-intercept, it's negative, negative y's. Okay, so where was our original x-intercept? 2. Okay, so because our asymptote, it's a fun word to say, was at x equals 2, that means the x-intercept was 2. Agreed? Sorry. They also give you another point, right? They give you a. And they say a is equal to 0 and instead of -0.25, what is that? -1/4. So could we figure out our original, our original y-intercept? It would be at -4. 1, 2, 3, 4. Okay? So y-intercept had to be at -4 because the reciprocal of -1/4 is -4. If you take the reciprocal of your reciprocal, you're back where you started. Okay, so this is good. Invariant points, we can plot the invariant points, right? When y was 1 and -1. Are we forming a beautiful line here? Gorgeous. So what's the equation? What's the slope? 2, because you're going up 4, right 2. So slope of 2. And your y-intercept we said is -4. So the equation is 2x minus 4. Good times? Okay, before we go over your quiz, let me just write down the assignment. If you need graph paper, there is some graph paper on the front table. The assignment is page 403 to 409, 1 to 5 CD, 8, 9, and 15. Okay?